Okay, lesson 3, solving logarithmic equations. So in order to use any of the laws of logarithms, the bases must be the same. And so you can see the power law, so just a little reminder of all the different laws that you know. The power law, if you have log base b of x exponent n, you can write the exponent at the front, and that's because with the power law of exponentials, you would multiply the exponent. So in logarithms, because a logarithm represents an exponent, you just multiply the exponent. Same idea. Product law of logarithms, if you have log base b of m times n, when you are looking at multiplying powers of the same base with exponents, you would add the exponent. So in the same sense, because a logarithm represents an exponent, you are adding the exponent values that are here. So you can rewrite log base b of m times n as log base b of m plus log base b of n. Quotient law of logarithms, same kind of idea. Log base b of m divided by n, whenever you are dividing powers, you would subtract the exponent. Because a logarithm represents an exponent, you would take log base b of m and subtract log base b of n. Okay, so you're sort of subtracting exponents because a logarithm represents an exponent. So remember that these rules apply both ways. So if you have n log base b of x, you can always write it as the exponent here. Or if you have log base b of m plus log base b of n, you can always write it as multiplication of the answer part. Or if you have log base b of m minus log base b of n, you can always write it as division between the answer part. So just a reminder of solving equations in general. Whenever you are solving exponential equations, the variable is part of the exponent. And so a lot of times when you are solving an exponential equation, you rewrite it using a logarithm to help you actually solve the exponential equation. So for example, if you have something like 7 to the exponent of x plus 2 equals 100, it's hard to get the same base here. So instead what you do is you take the log of both sides, and then you apply the power law and you solve it from there. Okay? So a lot of times when you have an exponential equation, you introduce a logarithm to help you. Okay? When you have a logarithmic equation, the variable is part of the logarithm. And so to solve a logarithmic equation, we can rewrite the equation in exponential form and then solve the resulting exponential equation. So sometimes, depending on what kind of problem you have, if you have an exponential equation, sometimes we use logs to help us. Sometimes when you have a logarithmic equation, sometimes we use exponents to help us. Okay? So here if you have log base 6 of x plus 5 equals 2, you rewrite this in exponential form as the base, which is 6, to the exponent, which is 2, and that's going to equal to the answer part, which is x plus 5. Okay? And then this is a lot easier to solve than the logarithmic form. Okay? So we switch between exponential and logarithmic form depending on which method is easier to use to help us answer the question. Okay, so there is a property of logarithms that we are going to look at, and this is only useful when you have the logarithm with the same base on both sides. So the following property may be useful when solving logarithmic equations, and again, this is only useful if you have a logarithm on the left side and you have a logarithm on the right side. As long as the log has the same base on either side, then the actual answer part must be equal to each other. It's sort of like when you have x exponent a equals x exponent b, which means a is equal to b. It's the same idea with logarithms. So if you have log of this base equals log of this base, then the answer parts must be equal to each other. Okay, so this is only good if you have a logarithm with the same base on either side of the equal sign. Other things that we might use to help us solve are factoring or the quadratic formula. And remember that sometimes when you are solving, you get extraneous roots, which are solutions that are not valid to the original equation. So we have a bunch of examples that we're going to go through. So the first example asks us to solve each equation. And so what you'll notice is that you have a logarithm on the left side and you have logarithms on the right side. So if I can combine all the logarithms on each side so that it's a single log on the left and a single log on the right, then what I could do is ignore the logarithm part and just look at the number parts instead, or the answer parts instead. So on the left-hand side, it's fine the way it is, but on the right-hand side, I can actually combine the logarithms together using the product law as well as the quotient law. So before I can use a quotient law, I need to make sure that this is all just a logarithm with no coefficients. And so what I'm going to use is the power law and bring the coefficient up as the exponent here. So I get log base 4 of 6 to the exponent 2 minus log base 4 of 3. Now if I simplify this further on the right hand side, I get log base 4 of x equals, now this will give me log base 4 of 36 minus log base 4 of 3. And again, I can simplify this more because I'm subtracting exponents. That means I could be dividing the answer part. So remember, a logarithm is an exponent. So this is one exponent minus another exponent. And so that means I could just divide the answer part that's here. So I get log base 4 of x equals log base 4 of 36 divided by 3. So this is using the quotient law. Okay? And so this gives me log base 4 of x equals log base 4 of 12. And what you'll notice is that because my logarithm has the same base, so I have log of something equals log of something, then these two parts must be equal to each other in order for the statement to be true. So this question is actually relatively easy. Therefore, x has to equal 12 is my answer. Okay, in this case, I have log of the square root of x squared plus 48 equals 1. And what you'll notice is in this case, I only have one logarithmic statement. So unless I can solve the answer relatively easily, what I will probably do is rewrite this in exponential form. So because it's a single logarithm in the entire equation, most likely if I write this in exponential form, it'll make my work a lot easier. So what I'll start to do is get rid of this square root part so that I don't have any roots to work with. And so I can rewrite that as an exponent of a half. And then what I could do here is apply the power law. So this will give me 1/2 log of x squared plus 48 equals 1. And then I can get rid of this half here so that I'm only dealing with the logarithm on the left-hand side. So then I can multiply both sides by 2 to get log of x squared plus 48. Remember to put the x squared plus 48 in brackets because the logarithm is being applied to the entire thing. And so that's going to equal 2. And now at this point, because I have log equals a number, I can change this into exponential form. So my base here is 10. So I have my base to my exponent, which is 2, equals my answer. And so I get 10 squared equals x squared plus 48. So that gives me 100 equals x squared plus 48, which means x squared equals 52 if I rearrange it. And if I square root both sides, remember it's plus or minus every time you take the square root, I get x equals plus or minus the square root of 52. Okay? And so this gives me two solutions. X equals the square root of 52 or x equals negative the square root of 52. And you want to make sure that both of these answers make sense. If I plug in the square root of 52 here, once I square it, it gives me a positive answer. If I plug in negative square root of 52, again, once I square it, it'll give me a positive answer. So both of these answers are correct. Neither one of them are extraneous. For this example, part C, I have log of x plus 2 plus log of 2x minus 1 equals 1. And so what you'll notice is that because I have logarithms on only one side of the equation, again, eventually I'm going to write this in exponential form. So before I do that, I need to make this into one single logarithm. And because I have addition between the logarithms, that means I have multiplication between the answer part. And so the left-hand side I can simplify to log of x plus 2 times 2x minus 1. Remember to have brackets around the entire thing since you're looking at the logarithm of that entire statement now. And so that's going to equal to 1. Now, inside the brackets here where I'm applying the logarithm, I'm going to simplify that a little. And if I actually expand and simplify that, that gives me 2x squared plus 3x minus 2. And that is equal to 1. Now, because I have a single logarithm here and I have an answer on the other side, it's hard for me to solve this unless I change this into exponential form. And again, because my base is 10, I can write this as 10 to exponent 1 equals 2x squared plus 3x minus 2. Bring everything over to one side, and I get 2x squared plus 3x minus 12. Okay? Now, if I'm trying to solve for x here, I can try to factor this, but this question is actually not factorable, so I need to use a quadratic formula. And so I get x equals negative 3 plus or minus the square root of b squared minus 4ac ends up giving me 105 all over 2 times the coefficient of 2 times a, which is 4. So there's my value for x, which means I get x equal to negative 3 plus the square root of 105 over 4, or x equals negative 3 minus the square root of 105 over 4. And if I actually figure out what these are as decimals, I get x equals 1.8117 approximately. And I get x is approximately equal to negative 3.3117. And now, if I wanted to check to make sure that none of these solutions are extraneous, I need to actually plug it back into here to make sure it's a logarithm of a value that I can actually evaluate. And so remember, you can only find the log of a positive number. So if I plug this into here, I get a positive result. If I plug it into here, I get a positive result. So what that means is this solution is fine. Now, if I plug this one in, if I do negative 3.3117, I get plus 2, I get a negative number. So right away, even though it might satisfy this logarithm, it actually doesn't satisfy either one of them in this case, but as long as it doesn't satisfy one of the logarithms in the original equation, then the solution would be extraneous. So this one here is extraneous. Okay, so I only have one answer for this problem. For our final example, we have log base 2 of x plus 5 minus log base 2 of 2x equals 8. And again, what you'll notice is that we have logarithms only on one side. So we have two logarithmic statements or expressions on one side. So again, eventually I'm going to write this in exponential form to help me solve it. So first thing I'm going to do is try to combine the logarithms. Because I'm subtracting the logarithms, that means I will be dividing the answer parts. So on the left-hand side, I get log base 2 of x plus 5 divided by 2x. So this is using the quotient law. Okay, now at this point what I can do is, because it's a single logarithm, I can rewrite this in exponential form. So I have 2 to the exponent 8 equals the answer part, which is x plus 5 over 2x. Okay, and now in order to solve this, I'm going to simplify the left-hand side. 2 to the exponent 8 is 256, and that's going to equal x plus 5 divided by 2x. Now, in order to solve this, because I have a fraction on the right-hand side, I'm going to draw my imaginary 1 on the left-hand side and then cross-multiply. And so 256 times 2x is 512x. And on the right-hand side, I have x plus 5. Now, if I'm solving for x, I would bring the x term over to get 511x equals 5. And so x is equal to 5 over 511. Okay? And I can check to make sure that this solution is not extraneous. So I get a positive number. If I plug it in here, it is fine. If I plug it in here, it's fine as well. So I checked it. Remember to always check to see if there's any extraneous roots. And that's pretty much it.